Okay, now that we know how MAC addresses work from the Part 1 video and the material you read in your chapters, because I know you did, we're ready to take that information about MAC addresses and learn how switches process MAC addresses when they're working on on moving traffic around a local area network, or perhaps forwarding to a router to go out into the web. So once away, I'm going to go away, and we'll start talking about switching fundamentals. An Ethernet switch is a layer 2 device. You need to remember that. And it issues uses MAC addresses to forward its decisions. A switch is not a smart device. It cannot remember or does not understand anything about the IP address. There's nothing programmed into it. It just knows how to read MAC addresses. And an IP address is absolutely useless to it. But it does MAC addresses very, very well, and that's important. Now, the MAC address table is a collection. As MAC addresses travel in and out the ports, it remembers where each of those addresses are and puts those addresses in a special memory called a CAM table. So when a destination MAC, if a computer sends a message in, and say from A, and it doesn't know where it goes, it hasn't seen that destination address before, it will flood it out all the ports except for the one where it came in. And then those computers will respond back. Whoever has that MAC address will communicate back. And then the switch will know, that guy's in port, what port it's in. So it fills in. So if D responds to A, then D's MAC address would go into the MAC address table. So here, port 1 knows that 00A is part of is out of port 1 on the device. And then it will build that table as it goes along. So here's the destination MAC is 00D, and 00D is over here, but the switch didn't know that, so it sent it out every port. D will reply, and then later on that will be put in the table. So the source MAC address is added when a message comes in, and then the destination MAC address is added as a source address when it responds. All right? So filtering frames when PCD responds, the switch says, oh yeah, that's who's out that port. Now, many computers can be out that port because it might be daisied to a hub, which connects to many computers, or another bank of switches. Who knows? So that address, that's how a MAC address gets built. And there can be lots and lots of addresses. Hundreds of MAC addresses can be handled, even thousands on some switches. So that's the MAC address table. And the destination MAC address, if it's not known, gets put in. All right? If it knows the address, it will only send it out the port where it belongs. This is a big deal. I go back to the days when switches were brand new, and they were very expensive. Just a little 4-port switch would cost thousands of dollars. But what it does is it breaks up traffic. Not every computer has to deal with traffic from every other computer now. It microsegments the network, and microsegmentation is a big term that you'll hear. So the collisions are avoided inside of a network because a switch can isolate traffic to just one device instead of many devices competing for the same wire. This was a big problem when, with the price of switches coming down, is not such a big problem now. So that's how MAC address tables get built inside of the switch. And as you can see, when the destination comes now, when A talks to D, the switch knows right where to send it and doesn't send it anywhere else. Now, in your curriculum, there are a couple of videos, and I want you to watch them. There's a demonstration on MAC address tables and sending a frame to a default gateway. And so I want you to know what both of those are by the end of this. Watch the videos in the online curriculum. You probably did it anyway because you read the chapter before coming here. Now, there's different ways for switches to handle traffic. They can do a store and forward and a cut through. And there's advantages and disadvantages to both. A store and forward switch gathers the entire frame. Now, to us, gathering a couple of bits in nanoseconds and milliseconds doesn't seem like a lot, but to a computer, that's a lot of time. So if it wants to store and forward, it will wait until the whole CRC is in there. That's the cyclical redundancy check. And that's a little calculation at the end where it can calculate to make sure the whole frame has been received, and that none of the frame has been lost to collisions or electromagnetic interference or something else along the way. We talked about that last week. So store and forward is very high reliability, but it's kind of slow. Cut-through switching is another method where it forwards the frame just as it receives the MAC address, and really doesn't, as soon as it gets the destination address, it starts to forward. It doesn't make sure the frame isn't invalid by either being a runt being too small or a giant being too big or damaged. So do you want speed or do you want quality? Those are the two methods, okay, that we talk about here. There's fragment-free is another one that is possible, where it looks at the first 64 bytes of a frame before forwarding, because that first 64 bytes, that's where the frame is generally invalid, because that all that's necessary to process it, the data, that other layers could deal with the data issues, but most network error collisions are in the first 64 bytes. So fragment-free switching can be a good way around that. Okay. So fast forward, didn't mention fast forward, lowest level of latency, all right, does it right away. Now we have memory buffering. Buffering is a bit of RAM that's saved for storing addresses and keeping frames in kind of in queue, like a corral, where we store these until the switch can process them. Because sometimes data will come in on a gigabit switch and it has to go out on a 100 megabit switch. That memory's got to sit somewhere. Pardon me, those frames have to sit somewhere while they get processed out. And we can do that either by port. You can assign memory so that every port has so much buffer, or you can have a big buffer that's shared by all the ports. And that really depends on the nature of the network traffic and what you as a network administrator would decide would be the most effective way for the data you expect to gather. Now, switch port settings can be duplex or half duplex. And you'll see these come up because when there's a problem, it'll tell you 100 times a second. Full duplex is when both sides of the connection can send and receive at the same time. And phone call, for example, you can both talk at once. But really, in radio communication, only one should do it so it can be clear. But half duplex is slower speeds and older equipment. You can only send or receive, but you can't do both at the same time. So if the duplex is full on one side, it needs to be full on the other. If it's half on one side, it needs to be half on the other side. Mixing and matching duplexes will not work. And newer switches have ways of auto-negotiating them so that it's not an issue. But in older equipment, sometimes you'll see where that has to go. And it also allows for the same speed path to go. The speed has to match. You can't have 100 megabits going one way and only 10 megabits the other. It just isn't going to work as far as what the NIC on the other end can handle. So the duplex speeds, the collisions will happen if it's half and full duplex. I explained that. Got to have that straight, but there is a way around it, and it's called Auto MDIX. Newer devices that have Auto MDIX can take that straight through cable that used to be a crossover cable and detect the kind of connection required, do the signaling, and fix it. So Auto MDIX detects what's needed, either full or half duplex, even what kind of cable you have in there, and then negotiates it accordingly. Now, 2 addresses are assigned to every device on the Ethernet. We've already talked about this, but we're restating it now because it's very important. Physical address, the MAC address, is burned into the NIC, and then the IP address is assigned by the administrator. And the IP address helps get that packet across the world to different networks. The MAC address is used inside the local network. That's very important to know. So if you're going to a remote network, the MAC address will change many, many times. Every time it gets to a device, it has to change because the MAC address is only good on that link. So the MAC address changes once on this. It gets into the router. While it's in the router, the router strips it off and looks at the IP address and calculates where it goes, and then decides which interface of the router to send it out. In this case, it's sending it out to R2. It puts on the MAC addresses of R1 and R2, source and destination. So it changes here. The source and destination MAC addresses are different here, and then R2 changes them again. And when it gets to the final destination, strips them away and goes up. So it's important to know the MAC address will change at every device, but the IP packet stays the whole way through. So while you absorb that bit of it and get through those videos in the chapter, we'll take a little break here, come back with one more section.